Okay, hello everyone. This is a joint session between the MESO, KIDS, and CEDAR. This is a substorm-ish related session, and I think we are going to start with Jason. Jason, go ahead.
As Bea said, this is a joint session between KITS that focuses on kinetic processes in the magnetotail during substorms, and MESO, which focuses on these mesoscale structures typically seen in both the ionosphere and the magnetotail. And so today's session is about how we can use low altitude and ground-based observations to figure out how all these processes connect to one another. Similar session information to the previous two, if you were at those. 7 minutes for invited speakers to present, 3 minutes for questions. We may not have time for all of the presentations, but we think we probably do if everyone stays on time. Don't hesitate to ask stupid questions, disagree with people, ask questions on Zoom. I'll monitor the Zoom questions. And yeah, we've got a bunch of different talks, outer radiation belt stuff, fast plasma flows, mapping, dipolarizations, auroral beads, and a bunch of other different mesoscale processes that have, or mesoscale structures that have kinetic processes associated with them. And we'll turn it over to Wei Chen, who's going to be talking about the outer radiation belt.
From here because I almost can't see anything.
Do you want to talk from below? I can give you the microphone.
Yeah.
All right, looks good online.
The middle button.
Okay.
This one will be this way.
Do you have a laser pointer? Yes,
I want. Have it? I don't think so. Does it have a laser pointer too?
So this go forward. Yes. This go backward. Yes, I see. But hold and point up like that. Point at that screen over there. So I can only point at. Yeah, go on stage. Go on stage. Go on stage using the mic there. Oh. Good morning, everyone. I'm Wei-Qin Sun from UT Dallas. Thanks for being here. And today I will talk about the energetic electron spectral at low altitudes, the transition from the plasma sheet to the outer radiation belt. The low altitude spacecraft cross the low altitude projection of the entire inner magnetosphere within several minutes and provide a unique opportunity to trace the dynamics in the Earth's magnetotail during substorm. And this figure shows the typical survey electron spectral observation from the low altitude. Survey provide two significant advantages, and the first one is a high telemetry efficiency, and the second one is a high energy resolution and sensitivities. So based on the simultaneous SEMIS observations, these two electron spectrum are confirmed to correspond to the substorm growth phase and the substorm expansion phase. In the lower panel, there is a localized relativistic electron population, which are clearly separated from the existing populations here. Generally, to figure out where these energetic electrons came from, we already look at the anisotropy distributions. But here, the electron measurement instrument on board survey, it has a look direction nearly perpendicular to the local magnetic field. So it mainly mirrors the flux perpendicular to the magnetic field, which represents the local trapped electrons. So here we try to use the pulse data to help estimate the electron anisotropy. And the lower two fingers shows the electron flux above 40 keV and above 130 keV from the pulse satellite, which is closest to the which is the closest in time and MRT to the survey spacecraft. And these two panels, in these two panels, each has two look direction, and one is correspond to the precipitating flux, and the other one is correspond to the trapped flux. And combining these two lower panels, we can identify the isotropic boundary should locate around 66 degrees here, as indicated by the black dashed lines. So we further did a detailed analysis on the electron spectrum during the substorm expansion phase. And this lower finger shows the flux energy profiles and different across part of the magnetic latitudes. And from these curves, we can see that these curves shows the exponential forms at lower latitudes and shows the power law forms at higher latitudes. At each M latitudes, we fitted these curves using such fitting function, which combines the power law part and the exponential part. To avoid overfitting, we set an upper limit of the characteristic energy E0, and the right finger shows the involution of the fitted spectrum. It clearly shows that exponential shapes at lower altitudes and evolves to power law shapes at higher latitudes. So to figure out where the exact location of the isotropic boundary, we further examine how the characteristic energy E0 varies with M latitudes. And in this figure, each red crosses represents the fitted E0 at different M latitudes. It shows a gradually increase and then raises sharply here. So to fit this trend, we use a singular function to fit this red crosses, shown as the black solid line here. The intersection between the fitted curve and the upper limit of characteristic energy E0 was taken as inferred isotropic boundary location, as indicated by the vertical solid, vertical dashed black line. It matches well with the isotropic boundary inferred from the pulse observation, which, it's shown as the magenta vertical dashed line here. So this good agreement demonstrates that the high-resolution flux measurement alone can be used to identify the isotropic boundary through the transitions in the spectral shape. We further extend our analysis to a more broader set of events, and this figure shows the statistic results from 17 substorm expansion phase events, and each of them shows a similar spectral transition from the power law shape to the exponential shape. And in this figure, each point compare the isotropic boundary locations inferred from the survey spectral and from the post-pitch angle data. They line up well with Y2X lines and indicating the strong agreement between these two methods. And here is the interpretation. We can understand it by thinking about how the electron flux, equatorial electron flux mapped to the low altitude, depending on their pitch angle distribution. If the pitch angle distribution is more isotropic, like in the plasma sheet, it will show the power law shape in the low altitude spectrum. However, in the alter radiation belt, the pitch angle distribution becomes more anisotropic, and especially at higher energies. So this will lead to exponential rollover at higher energies in the low altitude electron spectrum. So yeah, here in a word, the low altitude spectral transition directly reflect directly reflect how the pitch angle distribution varies from the plasma sheet to the outer radiation belt. It is the polar shape in the isotropic region and the exponential shape in the anisotropic regions. Yeah, that's all for this presentation. Yes, thanks for listening. Any questions?
I have a quick question if there aren't any in the room.
Hi, Jason.
Hey, so I guess I'm just wondering, and maybe you already went over this and it was too fast for me. Do you have theoretical reasons to suspect these functional dependencies?
Yes, sorry, I couldn't get it.
Yeah, do you have some theoretical motivation in addition to the fitting to justify the functional forms, or?
Yes, here I only show the overview of this function in the outer radiation belt, but based on our equation, it should have, the final function should have such a form that combines the polar law shape and the exponential shape. In the exponential shape, it's also related to the anisotropy index. Yeah, that's why we use such a fitting function in the previous case study here.
Okay. Okay, yeah, very interesting. Thank you.
Yeah.
Hello. Hi. So going from 2D spectra to the 1D spectra.
Here's this. Oh, sorry.
Yes. So I'm assuming that's the highlighted box.
Oh, sorry.
So you just take a time.
This panel?
Yes. So going from the upper 2D
Yes.
plot to the bottom one, do you just take the time average of the interval?
Oh, no, I didn't take it. Yeah, just plot the electron spectra and the exact latitude here. I didn't take the time average.
Oh, I was just asking, how do you go from that the top plot to the line plot?
Well, we just extract the flux energy profile along each latitude here.
Gotcha. Okay. Thank you.
Yes, thanks.
Okay, thank you so much. Larry, you can ask a question maybe after, find him. Thank you so much, Wei-Kin. We're going to move on. And our next speaker is Xiaoya. Oh, yay. Thank you.
Very remote technology. I hope I can handle this because there's no computer here. So good morning, everyone. I'm Xiaoda Zhang from UT Dallas. Today, I will be talking about mainly those electron losses as we observe from International Space Station. As we know that International Space Station, compared to other low-altitude satellites, it has a relatively low inclination at about 51 degrees. So that makes it projected to the equatorial magnetosphere up to an L shell of about 5 RE. So that's why this gives us an extensive data set to monitor those radiation belt electron dynamics using this data set. But why am I talking about this here? Because in this talk, we'll be mainly focusing on those electron losses driven by field line curvature scattering as is pertinent to the magnetotail dynamics. So here on the left-hand side, you are looking at the two data sets we'll be using here. So in addition to the International Space Station, we'll be also using the Alphen Mermans, which is also another low-altitude satellite with the pitch angle and the energy spectra for us to tune those integral energy channels at ISS. Specifically, we'll be using these two detectors on board the Japanese module of the International Space Station. So I will not go into details of these two detectors, but mainly talking about the characteristics of its measurements. So that the top one, the correlate, is mainly capturing those integral channels of multi-MeV electrons pertinent to image wave-driven precipitation. And this maxi channel in the bottom mainly captures those sub-MeV electron precipitation, and very similar to pulse, it has two look directions roughly corresponding to the locally precipitating particles and locally trapped particles. Gives us a better sense of at what condition or at what location the electrons are isotropic versus anisotropic. So in order to distinguish this field line curvature scattering from the other wave mode driven scattering, so we first of all, use these conjunction events between alpha and ISS to identify the signatures related to each of these two wave modes, namely those Whistler mode wave-driven scattering and image wave-driven scattering. So on the top panel, you are looking at this. Not sure whether I can point to it, but let me not do this, okay? The top panel are the alpha measurements, the locally trapped particles along the spacecraft trajectory, and the second panel is the precipitating to trapped flux ratio, identifying those precipitation intensity for each of the precipitation pattern we'll be looking at. So specifically here, on the left panel, you see that this weak burst precipitation, I probably have this one, related to this Whistler mode-driven precipitation. And in meantime, that you see that down at the third bottom, the maxim also shows this almost one-to-one one-to-one burst correlation correlated to the alpha observed precipitation bursts, indicating this localized maxi bursts can be used to identify this Whistler mode wave-driven precipitation along the ISS orbit. Of course, that we also can have this multi-MeV electron precipitation driven by Whistler mode waves, so that will add up some complexity here, so that we also can use this simultaneous measurements from correlate to identify this driven by Whistler mode waves. And the other mode that will be separating from the field line-driven scattering will be the image wave-driven precipitation. As you can see on the left-hand side is another conjunction event between alpha and the ISS. So we see that along alpha trajectory, we see this localized multi-MeV electron precipitation as a signature of image-driven precipitation. And in the meantime, that almost at the same magnetic latitude, that ISS or correlate specifically observed this multi-MeV electron precipitation in agreement with what alpha showed us in this event. So this kind of signature, this localized burst in the correlate data will be used to identify those precipitation driven by image waves. And to the last, that in addition to these two wave modes, we'll be able to identify those precipitation driven by magnetic field line curvature scattering. So specifically shown here are the two conjunction examples between alpha and ISS. You can see that as alpha captures this localized dispersive signature of this isotropic precipitation interval or signature. This is an indication of electron isotropic boundary along the alpha trajectory, right? And almost at the same magnetic latitude, again, that you see that this transition of isotropic to anisotropic electron flux at maximum moments on board ISS is a good indication that this most likely is also isotropic boundary or isotropic boundary for electrons. Interestingly, you can see that during this left-hand side event, this correlate which captures the multi-MeV electron precipitation also show a localized burst, slightly equatorward of this IB, but very close to it. Sorry, the arrow doesn't point to it. But on the right-hand side, you can see that this localized correlate measurements or correlate localized burst probably is slightly further away from the IB from MAXI, but more potentially related or might more likely driven by the image-driven precipitation, is also captured by ALPHN in this same orbit or in this conjugate orbit. So in short, that we'll be using this transition of this maximum measurements from isotropic to anisotropic electron fluxes to capture or to basically record the location of the isotropic boundary for electrons along this ISS orbit. So shown here are the 5-year statistics of all these 3 precipitation patterns we can identify, after comparing with the ALPHN measurements. So I will just point to the last panel here, which shows us the location of the isotropic boundary for electrons during this 5-year data set. So you can see that the black dots signify this location of the IB identified from SS measurements. So you see that the majority of these events are clustered on the night side, as we expect for this IB location. And also the red dots identify those points or those orbits with simultaneous relativistic electron precipitation, or better to say that multi-MeV electron precipitation potentially associated with the IB. That's pretty much it. So takeaway here is that we can see that there are quite significant orbits that shows this IB-driven precipitation or curvature scattering precipitation inside of 5RE, indicating that this field line curvature scattering can be a potentially important mechanism, not only in the plasma sheet, but also in the outer radiation belt, so as for it to really affect those multi-MeV electron precipitation or dynamics. Yeah, that's it. Thank you.
Thank you. Questions?
It's an interesting data set, Xiaojia. So one question I have is the one slide before this. As you mentioned, the curvature scattering is seen well within the inner magnetosphere, where the field lines are usually dipolar.
Yeah.
What do you think is the cause of current sheet scattering even such a dipole magnetic field?
Yeah, thank you for the question. So basically, as we also already seen in the ALPHN case study, so that this kind of penetration or deep penetration of this thin current sheet can happen during strong injection events. So most likely, we are seeing this kind of events along this 5-year data set. Yeah.
Any more question? No. Thank you so much.
Thank you.
We're going to move on, and our next speaker is Yang.
Okay, good morning, everyone. My name is Yang Shen from UCLA, and I actually gave the presentation in the Wednesday session, so apologies if you see any part of this presentation familiar to you. All right, I'm going to talk about linking redline auroral streamers to time domain structures and their potential connection with electron injection and breaking ion flows. Next one, okay. So magnetic field mapping is very important for understanding MI coupling. However, the commonly used signal model have known limitations during substorms. And one way to improve magnetic mapping is by physically linking auroral luminosity variations to wave-particle interactions that cause the auroral luminosity. For example, Nishimura et al. Use Coral's pulsating auroral correlation to identify the spacecraft footprint and to show that Coral's wave drive pulsating auroras. So here, this is a figure from Nishimura et al. The left figure shows Siemens ASI auroral image in white light, showing some pulsating auroral patches, and the right figure is the same format, but showing the correlation values. You see very small region of high correlation, which they identify as the true magnetic footprint. And these footprints are often different from signal model predictions. And this bottom panel shows the detailed correlation for chorus intensity and auroral intensity. So this method could potentially apply to other wave types, for example, time domain structures or TDS. So TDS have been recently identified as a potential driver for diffuse auroral precipitation, but it's still unclear what specific auroral features this TDS will produce. And so for TDS here, they are electrostatic broadband fluctuations in the frequency domain. But if you look at the data in waveform in the time series, you see that these TDS are actually millisecond scale, the biscale structures. So this is just a 1 millisecond time interval. And you see this red line showing bipolar parallel electrical field. These are called electron phase space holes, the most commonly observed TDS structures. And so TDS are often observed together with fast ion flows and electron injections in the night side transition region. Here we show the example occurrence distribution of TDS in the night side transition region based on combined observation from Van Allen probes and CIMIS. And so studies have shown that more than 90% of the fast ion flows were associated with the TDS structures if you have high resolution waveform data to observe them. And fast ion flows were also linked to auroral streamers. So that suggests the possibility that maybe TDS can play a role in driving certain types of auroral streamers. So here is one example we studied supporting this idea. So we have a conjunction event between CIMIS spacecraft and ground-based auroral observation, and here I want to show the observation in the magnetosphere from CIMIS in the night side transition region. This is during the recovery phase of a substone-like event. The plot is a little bit busy, apology for that, but the key features is that we observe Earthward ion flow velocities near 100 kilometers per second associated with electron injection around the time indicated by the vertical dashed line. If you can see it, it's around this time. And this is associated with, in this panel, the electrical field spectrogram showing very strong broadband fluctuations indicative of TDS structures. There were also relatively weak electron cyclotron harmonic waves or ECH waves. Both of these types are known to cause diffuse auroral precipitation. And based on these observations and the quasi-linear diffusion theory, we can predict the full precipitating electron distribution within the loss cone from CIMIS data. And we have published several papers on this result if you are interested. And integrate over energy, you can get the integral energy flux driven by different wave modes. So this is the precipitating energy flux. And this panel shows the characteristic energy of this precipitation from this distribution. And this red bar identifies the period when we have conjunctions with ground-based auroral observations. And the figures on the right just show example of the waveform data of TDS and the ECH waves. So these are conjugate auroral observations around the time of injection and ion flows. So the top panel shows ASI white line auroral image, and the bottom panel shows regal red line auroral image. Immediately after injection, we see black auroral and mostly diffuse auroral poleward of the black auroral, and the diffuse auroral were also observed the poleward of an auroral torch. But if we look at the red line emission in the regal data, we see that very structured streamer-like filaments moving equatorward, eastward, also poleward of the black auroral and the auroral torch. And these structures are what we call the red line streamer structures. And so the figures on the right shows an example of image of showing these red line streamer structures very clearly observed in the regal data. As you can see here, they are convecting this way without any electron acceleration features, by the way, but barely detectable in the white line image. And I also show the semi-magnetic footprint in comparison with the empirical signal model predictions, so they are quite different. Again, so we're using the method similar to Nishimura et al. To identify the magnetic footprint by examining the cross-correlation of auroral luminosity, the 2D pixels of RIGO, as well as the ASI, their correlation with the semi-estimated precipitating energy flux. So this panel shows the correlation value as a function of latitude and the longitude. So this is a RIGO image frame. You identify a very small region of very high correlation up to 0.9. This is a region we identify the magnetic footprint, and is about 1 degree in latitude different from the signal model predictions. So the figure on the right, the top panel, the red line shows the precipitating energy flux from Themis correlated with measured auroral, red line auroral intensity variations. And while the correlation doesn't mean causation, we can use Themis full precipitating distribution as the input to auroral transport code, T-Rex ATM, and forward simulate auroral. And to get the modeled auroral intensity, which is shown in the bottom panel as the magenta line, this is compared with the RIGO observation in black line, and we get fairly consistent results. So therefore, we conclude that the TDS-driven precipitation can well explain the red line auroral streamers. I'll stop here.
Thank you, Yang. That was great questions. Oh, I think everyone is happy to see this again. Thank you so much. We're going to move on to the next speaker, which is Natalia Kanushkina. S. Working? Yeah. This one. Oh, I see.
Interesting. We're recording, so it's really dark down here. So it's much better if you present.
It doesn't matter if
You don't care? Okay.
But I appreciate it.
No. This one.
Perfect.
Yeah. Okay. Good morning. I would like to present our initial results on the study of magnetic mapping during substorm growth phase. So we don't have any final products we can offer. So this is more than a proof of concept study, which I'm going to talk about. So the idea is to use ELFIN data. You've heard about that many times already during this week, and use electron isotropic boundaries observed by ELFIN during selected substorm growth phases, and then try to find times when we have Themis observations available in the night side MLT sector, and based on that, to introduce changes in basic Tsiganenko type magnetic field models by varying existing tail current sheet and incorporating new current sheets, fin current sheets, to be able to represent as best as possible substorm growth phase magnetic field changes. So isotropic boundary concept, I assume that everybody knows that, but for just in case, for those who are not very much familiar with this concept, this is a very brief, and I will say several words about that, the concept appeared from analyzing of NOAA-POES MEPED data, when we had on satellite two detectors, one parallel, one perpendicular to the magnetic field line. When we have a particle coming from the equator, and if it has significant small pitch angle, then when crossing the thin current sheet, it can be scattered and then precipitated. So if we look on the spectrograms, when the satellite comes from the low altitudes to high altitudes, then we see that we have precipitating particle flux is much smaller than the trapped particle flux. And then here, when they become comparable, this is the isotropic boundary. And then satellite goes over the polar cap and then again. So it happens, there's concept that isotropic boundary can be an indicator of the dynamics in the magnetotail appeared, and that was Viktor Sergeyev who said that can be an indicator, actually. So when the gyration radius of particle becomes comparable with a field line curvature, then the particle is exposed to pitch angle scattering. There is a conditions when the ratio between them is about 8, but this number is, again, approximate because it can range according to studies like from 3 to 33, dependent on where we are looking at that. Oh, what is this? I think yeah. So what I said about before, that was proton isotropic boundaries, and they were studied in many details. We are looking at electron isotropic boundaries, not so well studied as compared to protons. So we had several events, but right now I'm showing only one. Only one. What is it? Yes. So only one event on July 10th, 2021. So this is the example of electrons isotropic boundaries observed during that event. So we have data about 11 energies, and at the same time we had TEMIS measurements, and they were at about 10 Earth radii down the magnetotail. So to say exactly where is the current sheet, to determine its location in Z coordinate, it's challenging, and both if we're using magnetic field model or the data. So for this event, what we have, we estimate or reconstruct the low magnetic field from TEMIS measurements, assuming total pressure balance across the current sheet. So here, that's what I don't understand all of this. It's so difficult. So you see this reconstructed observed magnetic field and reconstructed low magnetic field on TEMIS. Here is this, okay. So here is this just for one energy, about 97.9 keV of electron isotropic boundary. You see these are several models of Tsiganenko type models, and what we show here is the difference between the observed and modeled. It's okay. I don't have many slides. So you see the difference between the observed latitude and modeled latitude of the isotropic boundary. And then you see the difference between magnetic field in the lobes. So we try to, if you see that this distribution is rather large, so we cannot say that any of the models fit well to recreate the observed location, MLT and isotropic boundary latitude. So, yes. So what we did, and we are not the first one. There have been several attempts to do that before, even back in the 90s. So we try to vary the existing current tail model, and these are the results for TS05. What we can vary there is the thickness, and then we can scale the intensity of the current sheet, and then we can shift the location, like the inner edge position. Here, what I show is the energy, the ranges of variations for thickness, position of the inner edge, and then scaling multiplier. So whatever we try to do, and these are three figures showing dependence on the difference between the observed and modeled low magnetic field, on the difference between the latitudes of isotropic boundaries modeled and observed. And whatever we did, nothing could bring this difference to the low values. So you see that's first one is for scaling multiplier for the current sheet intensity. Then second is inner age of the current sheet, and then the thickness. So just simple variations will not help us to get anything for substorm growth phase magnetic field. What we did that since, as I said, variations of the existing parameters doesn't help. So what we found useful is changing the profile of the current sheet. And here we take, in TS05, we vary this tail 1 module, and tail 2, here is this, on this figure you see this, all current systems, and then tail 1, tail 2 modules. This is X, Y, Z, and these are the more or less arbitrary values for current density. Just don't pay attention to the numbers. So these are the configuration. So if we try to introduce a different profile for a current sheet, and actually a family of current sheet modules with some discrete location, discrete L location in radial in the distance. So we see that actually to get a minimum error, and I actually don't have right now because it's ongoing study. I was not able to plot any of the magnetic field lines yet to demonstrate the actual difference between the observed, for example, observed latitude of isotropic boundary or modeled. But what we found to minimize the error, we see that our efforts, they result in putting the tail 1 module really close to the Earth and making it much thinner. That's actually my last slide. What we are going to do, we are going to, of course, apply all of this to all set of isotropic boundaries for different energies to find the energy dependence for that particular event. And we have several events to model this in the similar way, the magnetic field. And what I see here is it may be related to the previous talk about very close to the Earth isotropization observed at International Space Station. So that can be the reason, the case that actually current shade comes so close and it's very thin. And I think the recent models of Mikhail Sitnov and others also had this in their results. So this is it. I don't have any summary because that's ongoing effort, and isotropic boundary is quite a powerful tool to really tell us what's going on in the magnetic tail during different phases of substorms or storms or quiet, even quiet conditions. Thank you very much.
Thank you, Natalia.
Thank you. Natasha, thank you very much. Very interesting talk. It's not surprising that I woke up, I only have a stupid question. Beforehand, several groups tried to do similar procedure. Tuya, in particular, published in 1991 some paper with thin current sheet. Natasha Kubyshkina, what kind of thin current sheet model did you use in your tests?
Right now, we did not introduce any of the additional current sheet.
So this is just same Tsiganenko?
Yes, this is TS05.
Understand,
because
thank you.
First we try to see if there are any possibilities to change what is already available.
Okay.
But thin current sheet, which we had with Marina Kubyshkina, that was in 2004 or 5. That's
yeah, you hopefully know that Xiao Fei, she already published some results which show similar to yours.
Mm-hmm.
Thank you.
Thank you.
Thank you so much. We're going to move to the next speaker, who's Andrei Runov.
Mm-hmm. Okay, thank you. Well,
thank you everyone to staying here on Friday. I'm going to talk about THEMIS observations in the near-Earth plasma sheet during so-called HILCAS events and observations on conjunction ionosphere, ground-based magnetic observations. So first of all, HILCAS, it stays for high intensity, long duration, continuous AE activity. Blame Bruce Surutoni for this awful acronym. This slide shows, whoa, so big. Typical behavior of IMF, 3 upper panels, the solar wind velocity, density, and geomagnetic indices during HILCAS events. You may immediately see very fluctuating magnetic field, interplanetary magnetic field, and believe me, these are alvenic fluctuations. I did not plot total field, sorry for that, but you can judge from density. Interestingly, yeah, well, okay, next point to see these high-speed flows, high-speed streams in solar wind. Why it disappears? Density was stay relatively low until this point. Sim H was relatively low again until this point, but look at that. AE was pretty high. It's 1500 here during very long time interval. That's what we call HILCAS. HILCAS actually famous for cooking radiation belts, fluxes of relativistic electrons extremely increased during HILCAS. But what we found that even beyond geosynchronous orbit, we have highly increased fluxes at energies higher than 100 keV. These are data from THEMIS SST, captured at axis beyond larger than 7 RE. So energy here is higher than 100 keV. So it's relativistic fluxes in near-Earth magnetotail. The right-hand panel shows the spectra collected during intervals highlighted by red bars here. You see that we have quite appreciable flux. There's a differential energy flux, differential particle flux versus energy. We have quite substantial fluxes at energies higher than 100 keV, way above the background, which is black, and 1 count level of the SST instrument, which is a green curve. Well, what THEMIS observed at that time? Plotted here are magnetic field, 3 components, BZ, probably most important, is in red, electric field from EFI instrument and THEMIS, electron and ion energy time spectrograms, density. I deliberately keep ion and electron density plotted together to show quality of the data. Ion and electron temperatures, and finally bulk velocity observed during one of the highlighted events. What is interesting here, you immediately see in magnetic field kind of growth phase, which was like about 20 minutes long, during which the BZ drops to very small values. Then immediately after that jump in BZ, huge electric field. It's 40, 60 millivolt per meter, believe me or not. That strong electric field associated with this dipolarization, drop in density, increase in electron temperature, and oops, sorry, wrong button. Can I go back? Yeah. Vortex-like plasma motion in the magnetotail. Themis was at about 10 RE down tail. The onset happens at around 0500 UT here. And what is interesting that at that time, energy of electrons, flux of energetic electrons dramatically increased, which actually reflected in the temperature. At the same time, at around 5 UT, GOES observed increase in, also kind of step-like increase in fluxes of more than 2 MeV electrons. What happens on the ground at that time? Again, remember, onset of dipolarization at Themis happens at roughly 05 UT. Here is the, oops. Here's dashed line indicating dipolarization onset on Themis. And immediately after that, at Fort Churchill, which was in conjunction, we see quite substantial magnetic variation called geomagnetic disturbance. And the right-hand panel shows reconstructed equivalent ionospheric current. We see development of pretty strong and localized current system during that time. Well, and in summary, during Hilka's events, Themis observed repetitive substorm-like activity with stretching and dipolarizations and electron energization to relativistic energies during dipolarizations. At geosynchronous, we observed rapid increase at relativistic electrons. And on the ground, the geomagnetic disturbance, everything roughly in 2 minutes. What is interesting and what is the link between electron energization and geomagnetic disturbances is that factor of 5 increase in electron temperature. If you remember night relationship, it has a parameter of electron temperature here versus basically density. So increase in electron temperature may lead to local enhancement of Hall conductance in the conjugated ionosphere, which may then cause the strong diamagnetic disturbance with quite significant dB by dt, which was indeed observed at Themis, near Themis footprints. This work was published. Here is the reference. That's it from me. Thank you.
Hey, thank you, Andrei. That was wonderful. Questions?
Thanks for a great talk again. My question is, you said that the dipolarization is substorm-like.
Yeah.
What would you, why is it not a substorm?
Well, that's probably a question of definition what substorm is. If it would be individual substorm, isolated substorm, I would probably call it substorm. However, the cycle is shorter than typical substorm. It's just one example, but we have lots of them repeating in kind of 20 minutes, half an hour cadence. So it seems that its behavior of very near Earth plasma sheet thinning first, then dipolarization. So it's kind of repeating substorms.
Could I ask a related follow-up question on that?
Go ahead.
So I guess this seems like a more localized current structure than a substorm as well, right? I mean, do you think that there's going to be a global current wedge or just this localized structure that lasts for 20, 30 minutes?
Yeah, that's precisely what I'm trying to say. If you may see it from the geomagnetic measurements, or maybe specifically from reconstruction. It's very localized structure.
All right, yeah, very interesting, thank you.
So this is what you'd expect if you saw a series of streamers. You often just see a series of streamers, every 30 minutes coming down in the auroral ovals. This is exactly what you'd expect to see for that situation. Of course, you don't have auroral measurements showing that that's actually what's happening, but that's what I would expect. That would be my most likely guess as to what's happening.
Yes, in a companion paper published by Mark and Gebretson, we published, I guess Toshi supplied us with auroral images. Yeah, we clearly see also isolated auroral structures. I'm not sure about streamers, but yeah, Toshi may correct me. PBIs.
I think I said you see PBI and streamers.
Those stuff that you would usually expect. So, sorry for those who couldn't hear. So I was saying that there are indeed PBIs on bright streamers. So particularly at the polar boundary, we tend to see this kind of strong currents with strong DBDT, and that I think those are nicely related to the injections, as Andre showed.
Thank you.
Thank you so much. We're going to move to the next speaker, who is Sanjay Chapuri. Yes.
All right, thank you. All right, thank you. So today I'll be talking about some ongoing work looking at the partition of energy flux transport at bursty bulk flows. And since this is a quick talk, my poster, Wednesday number 22, will be up for a couple more hours, so you can go check that out if you're interested in looking more. So first, very quickly, bursty bulk flows, I think probably a lot of you know this, but for those of you who don't, they're these high-speed earthward flows, last few tens of minutes. And sort of the key point here is that it's been shown that these are responsible for a large amount, maybe I may even say most, of the energy transport through the tail earthward, mostly during these flow bursts. And they sometimes are accompanied by injections, but not always. So the question that I'm asking here is how, when we do see these BBFs accompanied with injections, how does the energy carried earthward by those two different populations compare with each other? Because then that could have implications for the energy transport when, for example, we see one but not the other or something like that. So the first question we have to ask here, well, is to define the energy flux and define those different populations, like I said. So starting with the energy flux, so I used MMS for this project, and I want to calculate the kinetic energy flux at MMS for these different populations. So when I say, so like the energetic versus the thermal population, the electrons versus the ions. And I also want to compare their Poynting flux. And I defined the kinetic energy flux using this fairly simple equation from Lee et al. So what this looks like here is an example event. Can I use this down here? No, okay. So yes, this is one event that I looked at. You can see in the bottom panel is the ion velocity. So you see like sort of classic BBF signature with the ion x velocity, so earthward velocity of a few hundred kilometers per second. And then at the time during these flow bursts, I took the energy spectrum of the ions that's graphed on the right there, or on the left, depending on your point of view. And so, like I said, the first thing I need to do is to define the different populations. And based on this energy spectrum, that was a little bit difficult to disentangle them, the ion injection versus the thermal plasma flow. So what I did, this is just as like a sort of a first guess, is I took the ion plasma temperature and doubled it. Said, okay, once we're double the temperature, if we have a thermal distribution, likely that thermal population has like largely died off by that point. So anything above, in this case, 20 keV, that's twice the temperature, we'll call energetic. Anything below 20 keV, we'll call thermal. And so I graph in that third panel down, I graphed the energy flux from the two different populations as well as compared to the Poynting flux during this time. And if you look at the black thermal line and the green energetic line, during the time of the flow bursts, they're roughly the same order of magnitude. So that's saying, okay, these two populations are both responsible for a significant amount of the energy transport. But that was like a pretty hand-wavy definition of thermal versus energetic. So I looked to see how sensitive changing that threshold was, and the answer is unfortunately pretty sensitive. So, like I said, this is still ongoing work, so I'm still trying to come up with a better definition way to separate the thermal and energetic populations. But what I've done for now is sort of like turn that question on its head and say, okay, what if instead of like trying to separate the populations, let's just look at the energy level at which the energy transport from more energetic than that energy and less energetic than that are contribute equally to the energy transport. And when I did that for a couple different events, I graphed that here as a function of the ion temperature. So this is only 7 data points, not a ton, but I think it's looks pretty clear that that just follows a straight line with the ion temperature. So all this is doing is giving us a measurement of the ion temperature, which makes sense if it's the thermal plasma that's contributing. But these two red dots on this graph are events for which I concluded that there are ion injections occurring. And you would think if this energetic ion population was contributing significantly, those two red dots would be off of that line, and they're not. So this is giving at least a preliminary, I say preliminary on here, a preliminary suggestion that for ions, the thermal plasma flow contributes significantly more than the energetic ion injections to the energy transport earthward. But like I said, I still want to do more work with characterizing the different populations and try to measure that in a more direct way. The next step is to look at electrons. And for electrons, I was much more easily able to separate out the two populations. So if you look again on the left from your point of view, again, I graphed the energy spectrum in black, and on top of that, I have plotted in blue the spectrum you would get from a Maxwellian distribution. So you can see pretty clearly it follows very closely up until, in this case, it's around 7 keV or so, when the Maxwellian drops off and the observed spectrum flattens out into the power law tail that you expect, in a Kappa distribution or something like that. And so we can pretty clearly say, I have that line plotted there. Anything more energetic than that line is, characteristic of our injection population. Anything less than that line is our thermal plasma core population. And so I did something similar where I calculated the energy flux for the two different populations. And I have plotted in the third panel, you almost can't even see it because it's so dramatic. But if you look down on the fourth panel is the ratio. The ratio of the energetic energy transport to the thermal energy transport. And you can see that it shows that the energetic electrons are responsible for several orders of magnitude more of the energy transport than the thermal plasma. So this is needs to be confirmed still, because actually most of the work I've done on this project so far is related to taking the existing FPI plasma moments, adding on plasma moments for the Phoebes energetic electrons and combining them. So I've done a lot of work on that. I think I'm right, but I still need to fully verify that I've done everything correctly. So this is not 100% yet, but if it's even close to right, which I think it is, at least close to right, it's showing that the electron energy or the energetic electrons are much more relevant in this case than the thermal electrons. And then once I do get everything I've verified, I trust this number 100%, then I can compare the electrons and the ions and see, all these populations together, compare the Poynting flux, see, sort of disentangle what is actually most important. Yeah, so like I said, it's ongoing work, so here's the future work. I also will, look at some more, I just looked at a couple of events that, sort of look nice. So I'll look at more targeted events. What I would love to do is see if there's a multi-point observation where we observe an injection in the inner magnetosphere and sort of compare that. I compare types of parameters like solar wind, geomagnetic activity, look at storm time versus non-storm times, things like that. But yeah, so I'm happy to answer any questions. If anyone has any, like I said, this is future work, so if anyone has any ideas for something I should look at, I'm happy to hear it. Yeah, thank you for listening.
Thank you, Sanjay. Questions, comments, suggestions? Thais.
Thanks for an interesting talk. Have you compared the energy transport in flow bursts to that of just a quiet time tail without the flow burst? What's the ratio?
I haven't, yes, that's, a good idea, something to look at. Thank you.
Any more questions? If not, thank you so much again. So our next speaker is Sheng Tiang, but I think, oh, you're here.
Is it possible that I share screen?
Yeah, I think so.
Okay, let me try. Okay, can you guys see my screen?
Not yet, probably soon. Yep, there we go.
Okay, great. Yeah, good morning.
We're not seeing your slides here.
Oh, no?
Wait a second. Now we're ready.
You're seeing my slides right now, right?
Yes, yes.
Okay, great. Yeah, it's a pity that I cannot go, but thanks the conveners to give me a chance to share the updates over Zoom. Yeah, so today I'll talk about discrete aurora and high altitude driver. So I'm showing discrete aurora measured from different planets to just note that it's interesting that it's not only Earth. Aurora is, and discrete aurora is a universal phenomenon. But really, if we want to understand deeper, we have to go study Earth. So just a brief introduction. Morphologically, aurora can be classified into discrete, which is structures in bright, and diffuse, which is relatively homogeneous. And diffuse aurora is simple. So as Yang just mentioned, we have waves scatter electron around the equator. Those electrons precipitate, and then we got diffuse aurora. So diffuse aurora is related to electron scattering, whereas discrete auroras are related to electron acceleration somewhere along the field line, which I'll talk more in detail. So this is adopted from the flyer of FAST symposium early this year. It nicely shows the major findings of the FAST mission, which is the two auroral acceleration mechanisms. One is from quasi-static potential drop, and the other is from dispersive alpha waves. So basically, E parallel that's static and fixed in low altitude. The other is from wave and travel in space along the field line. So so that's all good. But if we move to higher altitudes, things start to be more unclear. So we talked about discrete auroras. There are many types at ionospheric altitude. Then at fast altitude, we know there are two acceleration mechanisms. And we also know that at very high altitude around the equator, we have alpha waves, slow bursts, dipolarizations, etc. So how do they connect? That's much less well known. And one major problem is we do not know where high altitude spacecraft maps to, because it's just the uncertainty is significant, and to make things even more complicated, we have dipolarizations. So the flux tube move around, so it's even harder to get a good mapping. And the other problem is for high altitude spacecraft in polar orbit, for example, polar and cluster, they measure both temporal and spatial changes. Whereas for fast, it's relatively simple. At low altitude spacecraft, it just mostly measures the spatial changes. So for high altitude, it's hard to interpret what you measure. But we do have some idea of what's happening at high altitude. So this is an example showing the good statistical relation between alphanic Poynting flux and the average auroral intensity. So in some way, we know alpha waves are important in driving the oval on large scale, but I'll talk more in the next slides that at this time of the research, we still don't have the necessary information to look at the correlation at mesoscales, which is required for discrete aurora. So the main question that I'll discuss here is what are the high altitude drivers for discrete aurora? And there are two major improvements that allow us to study this now. First is technology. We have much better auroral images. So here is an example of what we have now from all-sky imager in comparison to the old era. So this is a streamer, this is a streamer. We can clearly see it's much well resolved. And this is speeds, same thing. So we have basically an order of magnitude higher spatial and temporal resolution to resolve the structures and also to resolve their evolution. The other thing is, I think it needs more discussion because I think it's not very well appreciated. So many previous speakers already talked about mapping. So in this case, we try to use magnetic models to do mapping, either inward mapping or outward mapping. But the problem is the same. Although we have relatively small uncertainties in local time, the uncertainty in latitude or distance is pretty large. So in this case, the four-Synchronenko model, the uncertainty is 5 degrees, whereas the arc is just less than 1 degree. So how do we do about it? Maybe, so this is what I want to try to convey here. We can do no mapping. So in this case, this is more than 2 hour long data from RBSP. So we can see from the kilogram that aurora goes, growth phase goes to lower latitude and then poleward expansion and do the same thing again. So we see two subswarm cycles here. What RBSP see is two dipolarizations here associated with the first expansion and the second one with the second expansion. And also we see electric field, very large, and appear here, here, here. So what this means is that, so imagine RBSP is somewhere in front of the fireman. So this hose, although it depolarizes and comes down multiple times, we don't know where it goes. But if you sit there, you get wet twice when it goes up and down. And this is exactly what RBSP does. It sits there and it sees the electric field. In this case, is just the water, right? The flux tube depolarized, it passes up RBSP, and RBSP sees something, and then it goes down, sees the electric field again, it goes up again and sees the electric field again. So using the temporal correlation between aurora and data from an equatorial satellite, so we can do this kind of temporal correlation and identify high altitude conjunctions directly. So this is like a physical information from the benefit of equatorial satellite, because they essentially stay around their apogee for hours. They don't move much. All what they're measuring is temporal changes. So we can compare that to the aurora's temporal changes. And this is much more information we can use to identify, ambiguously identify conjunctions. So using this technique, we go ahead and look at first auroral beads. And in this case, we have auroral beads and RBSP sitting somewhere here around the equatorial plane. So if we look at the eogram, individual beads will drift in local time and show as stripes. And for those two beads, we see two electric wave packages. So that's a suggestion that the spacecraft is in conjunction with the beads. And from there, we figure out what's happening along the field line of the beads. So first, we have alphanic acceleration and alpha waves around the equator. We start to have some alphanic acceleration that accelerate electrons to several hundred eV. And then off equator, we have more alphanic acceleration and accelerate those electrons to several keV. And then those electrons precipitate and give us the beads. So in this way, we identify that kinetic alpha wave is driving the auroral beads and via alphanic acceleration and at multiple altitudes. So the other thing that we've checked is discrete arcs. So this is the example that I showed you earlier. And for this time of the first expansion, we look at the data in more detail on the right. So we see the expansion, and this is the auroral brightness. And then around this time, we see a short burst of very large earthward pointing flux due to alpha waves. And this is the arc passing the foot point of RBSP. So from this temporal correlation, we can see alpha wave is the high altitude driver for discrete arc. And for another event, we do the same thing. And in this event, we have even more information. So first, we have alpha wave observations around the equator. And then we see the ion outflow, O+ outflow. It's dispersive, and it gives information of the time of flight of those ion outflows. So then we can figure out they're coming from northern and southern hemispheres. And then at low altitudes, we have the MSP pass, measuring the inverted V electrons. Both the electron and outflow measurements suggest there is a potential drop somewhere here. And in the end, we have see the arc in northern hemisphere and southern hemisphere with very similar shapes. So from this event, we'll argue that alpha wave drives discrete arc, and it's via a quasi-static potential drop. So summary, what do we know about discrete aurora now? So it's like a game. Before we have a lot of unknowns, and then we start to connect many of the components. So beats, alphanic acceleration, and alpha wave potential drop, discrete arc, things like that. And there are clearly more we can do because there are still more types of discrete arcs, and also we know that there are more high altitude drivers that may be connected to a generation of alpha waves. Yeah, so I'll stop here and see if there are any questions.
Thank you, Sheng. Questions in the room? I know, Jason, you have a question. I see your hand up.
Yeah, if there's none in the room. I guess I'm confused because the Alfvén waves are field aligned mostly, so I understand the acceleration part, but the bead structures are transverse to that. So aren't the Alfvén waves just transmitting the equatorial wave pattern down to the ionosphere?
You're right that alpha waves are traveling parallel. So I think the beads is just a magnification of the azimuthal development of alpha waves. So each bead, the bright spot is one spot where you get strong alpha wave.
But what is it? Sorry, go ahead.
And beats develop azimuthally means that there are more alpha wave develop azimuthally, because the travel time of alpha wave is negligible.
Right. So you think that there are Alfvén waves structuring both the beads in the equatorial plane and transmitting them down to the ionosphere?
Exactly. Yeah.
Okay. All right. Thank you.
Okay, we're going to move on to the next speaker, who's Tetsuo Motoba.
Hi, my name is Tetsuo Motoba. So today I would like to talk about a link between the mid-scale oral streamers and geosynchronous dispersions injection. So, can I move? Okay. So this is a brief introduction. So historically, using the Los Alamos satellite data, the geosynchronous dispersions injection region was suggested to span a wide MLT region around local midnight. But recently, high-resolution imagery simulation showed that the mid-scale structure in the magnetic tail is a primary feature of particle transport into the inner magnetosphere. So, However, it remains to be understood observationally about how the mesoscale multiple material structure are connected to the geosynchronous injection. So in this talk, using the THEMIS ASI and GOES data, I would like to show an example of isolated substorm event. So what I'm showing here on the left side, no, it's difficult to control. But the left side, the supermag oral indices, SMR, SMU, during the isolated substorm event, which took place on the January 14th, 2018. So you can see the SMR drop around here, so which is a substorm onset. So on the right-hand side, I just show the THEMIS oral movie during this event. So as you can see, so let me go back. Blue line is a midnight. So and this time as a substorm onset occurred, and then we can see the westward traveling surge. After that, the poleward expansion and the bulge developed. So around the expansion phase, we can see a lot of oral streamer at different local time. So I just want to compare such the oral streamer with the GOES data. So, I just focus on this yellow shade time, about 10 minutes. So this is the first time. The top panel shows a snapshot of THEMIS oral image. So, and the bottom panel is show the GOES data and the magnetic field and electron flux and the proton flux. So first, this time, red line is just this snapshot time. So we can see, during this time, at this time, the GOES oral streamer appear only around the GOES 14 meridian. So at that time, GOES 14 observed dipolarization front on the red curve and also the dispersionless injection. However, at GOES 15, did not observe any signature of the dipolarization front and the dispersionless injection. So next time, the signature is opposite to the previous time. So in this case, we can see the oral streamer appear only around the GOES 15 meridian. So at that time, GOES 15 observed dipolarization front and dispersionless injection. However, GOES 14 did not observe such signature. So this last time, and in this case, it's a very interesting signature. At that time, the two different oral streamer propagate around the GOES 14 and 15 meridians. So at that time, both GOES observed the dispersionless injection simultaneously, but which that dispersionless injection caused by the different streamers. So in summary, as shown here, whether or not GOES observed dispersionless injection is related to the presence or absence of mesoscale or streamer near the GOES meridian. So if the aurora streamer is a tracer of BBF and dipolarization front, so this observation suggests geosynchronous dispersionless injection is a direct mesoscale BBF DF impact rather than the injection boundary. So as shown here, such the coordinated ASI and GOES observation provide a unique opportunity in the understanding the role of mesoscale structure in the tail to the geosynchronous injection. That's all I have.
Thank you so much. Yeah, give you the microphone.
Yeah, that was very nice and very, very clear, very definitive. I really enjoyed that.
Thank you.
One other thing you could do is that instead of just showing the supermag L index, if you look at the ground magnetometers as close as you can to the individual meridians of those particular streamers, you should see the, the magnetic field drop associated with that.
Yeah.
Which will further emphasize the sort of mesoscale nature of that, and also emphasize that what we used to call a substorm is really a streamer, and that the substorm onset, which you had, is sort of happens earlier than all that beautiful action that you were showing.
Yeah.
So I like that.
Yeah, thank you very much. Yeah, will do.
Hi, over here. Yeah, it's Christine. Thank you for the lovely talk. So my point is just that I think we make sure we have some caution, because what we often see is, like, if you're associating streamers with the mesoscale flows in the tail, often those mesoscale flows in the tail, they are coming in and then they break, and then we have the large scale dipolarization, and then they never make it into geosynchronous. And so you could have the ASI signature that shows the streamer, but then there's sort of like some intermediate steps between that initial streamer or fast flow that then in the magnetosphere kind of could have become part of a larger dipolarization, which then moves into geosynchronous to cause the injection at GOES. I don't know if you have any other comments or thoughts about that.
So cannot point here. So first, this white line is a substorm onset. And then we can see it as westward traveling surge in the movie. At that time, it's difficult. So GOES 14 observed global scale dipolarization. And also, we can, as I shown here, there's some transient BBF and DF cause the transient injection, but I'm not sure. It's the injection level, flux level is just 1 minute increase and suddenly decrease at that same level at previous one. So how, if we have some satellite inside the geosynchronous orbit, we can see more flux enhancement. But at this event, we cannot see such a contribution.
Got it. Yeah, thanks for that. I definitely agree with you. If it's these just smaller scale flux enhancements, that's not the large scale dipolarization. So sorry I missed that, but thank you for clarifying. Yeah.
Quick, maybe not that quick. First, thank you very much. Very interesting talk. Can you go back to your conclusions, please? Yeah, I'm specifically interested in second bullet. It's actually a very long-standing question. What is injection boundary and how injection boundary related to individual point of stop of whatever BBF, DF, name it. And it's maybe related to, well, maybe Larry's comment. With all due respect, I disagree that substorm is just a streamer. No, it's a global dipolarization, and we know it since, at least since beginning of 80s. We know that the substorm, or the dipolarization, better say, propagates duskward and downward in 20 minutes and cover finally up to 10 hours of MLT. So it may be point of, discussion for further. How do we relate these mesoscale signatures to more global scale phenomena like substorm? Any ideas?
That's a good question. So, but as I shown in the movie, we can see some westward turbine surge just after the onset. At the westward turbine surge expand the westward. At that time, goes satellite observed large-scale dipolarization. So I'm not sure. We can see that large-scale dipolarization, but in the large-scale dipolarization, we can see some localized structure in the injection and the dipolarization front. Did that answer? Oh, okay, we can talk offline after my talk.
Yeah, so I like what you just said, because you see the sort of a larger scale dipolarization. This is built upon it. Anytime you have an injection, into geosynchronous orbit, you're into the transition region. So it's a bubble of low energy plasma. So the magnetic drift is going to carry those energetic ions, off to the side. So any localized structure which appears impulsively initially is going to spread as a muthilate. And so particularly so any one is going to spread and become larger scale. And particularly if you have several, like I think you're implying, you're going to get a pretty large scale current wedge. I think it all kind of fits together just based on if you consider the azimuthal expansion of the bubble that's been injected.
Yeah, I think it's important to distinguish, though, what we call a substorm, which is this global phenomenon that encompasses many of these smaller scale structures, and not call every flow burst that reaches geosynchronous orbit a substorm, because that's simply not the case. There's many flow bursts that occur outside substorm periods, and there's many flow bursts inside a substorm like you're showing here, a very nice example of. But to be a substorm, you really need that global expansion both in the ionosphere and in the inner magnetosphere of the dipolarization front azimuthally.
Yeah, I agree.
Thank you so much, Tetsuo. We're going to move on to the next speaker, is Shan Wang.
Hello, everyone. My name is Shan Wang. I work at Peking University. Today, I'll discuss our trials on decoding convection from substorm processes with MLT patterns of these indices. So I think that for substorm, we always need a thin current sheet in the magnetotail. So the big question we ask is what is the mechanism for driving the thin current sheet in the magnetotail? Oh, I see. Okay, thank you. So this is the most traditional mechanism that after day-side reconnection, the downG cycle brings open field lines towards the magnetotail, and the flux is accumulated in the lobe, which compresses the current sheet to make it sink down. This is another mechanism due to flux depletion. So once the global convection is enhanced, the flux is depleted, so the pressure here drops, so that current sheet can be sink down. The two processes should come along together, but there might be a difference for the relative importance between the two. And then for this case, it really requires enhancement of the global convection. So if we have any signature for this convection, we might be able to distinguish the importance between the two. So that's the motivation of this study. The convection has corresponding signatures in the ionosphere. The two-cell convection pattern corresponds to the dp2 current, which can be manifested in the SMU index on the dusk side and SML index on the downside. But the SML index is more complicated because it represents the main magnetotail current wedge dp1 current signature. This paper by Otani et al. Also studied the SML on the downside, SML06. Some events have significant enhancements of this index. They provide 4 types of interpretations, which include convection and the downside current wedge. So here we have 3 goals. First, what I just showed is just a scenario. Can we have more direct evidence to connect between the SMU or SML index and the global convection? Second, can we just categorize the SML negative Bay events, the substorm-like events, using these patterns to distinguish those with strong or weak convection? Then we can make some comparisons between the 2 kinds of events. So we use this so-called self-field algorithm to gather the events. Basically, we have these negative Bay events of SML, and then we will do some classifications. So for the first simple classification, we use the ratio between delta SML and delta SMU. Delta means the difference between the onset level and the extreme values during these events. Then the left side shows the supposed epoch analysis of the MLT distribution for SSMU and SML indices. The left side is for high delta SMU events, and this is for low SMU category. So you can see there's more enhancements and in SMU, which is indeed near MLT of 18, consistent with the global picture. So we might expect that the left-hand side events have more convection. What I mean by more direct evidence is from this scenario here. If we have a shear flow in the equatorial plane corresponding to the two-cell convection, that can generate field line current, and field line current corresponds to auroral precipitation. So if we can find evidence from these signatures, that might indicate convection. So we gather the data from DMSP SSJ electron precipitation for 2 types of events. They are further categorized by their instantaneous SME index so that the polar cap size can be similar. This first row shows the results for high delta SMU category, and then the second row shows the difference between 2 types of events. So you see most is in red color, which means high delta SMU events have more auroral precipitation. We are not showing it here, but we also test with the ampere field line current data, which show similar things. That means high delta SMU events indeed have stronger aurora and stronger field line currents, so they indicate they are indeed having stronger convection. Then we try further classifications, including the timing information of the index. For SMU, we have 5 categories. This low means SMU index is low throughout the event, and high means it's high throughout the interval. Then for the right-hand side, these events have a peaked profile of SMU, but the timing can be different. The peak can occur prior to the substorm onset time, or peak middle means the pace of SMU and SML enhancements are similar. And in the last case, peak late means SMU enhances much later than SML. So if we care about the contribution for substorm onset, both low and peak late events have weak convection near onset. So this is a superposed epoch analysis of the 5 categories. I will only emphasize one thing. So the green, blue, and magenta curves are for peak early, peak middle, and peak late categories. They correspond to the timing of southward MFBZ shown in this panel. So here is the green, blue, and magenta curves. So the longer duration of negative BZ makes the SMU peak delay. That's the correlation. The SML pattern is more complicated. So sometimes in the most simple case, it's only enhanced near midnight here. And the N2D means the primary enhancement is near midnight, but it can extend to the downside. For the following 3 categories, you can see there are 2 separate enhancements between midnight and downsides, but the timing can be different. This is the best guide. This is a clear case where the primary enhancement is near midnight, but the separate enhancement on the downside is weaker, but it occurs prior to the night side enhancement. So I interpret this downside enhancement as the signature of global convection, and that can contribute to the status near onset. So then these 3 without strong convection, I call them weak convection, and these 2 mean strong convection. We have a whole other category where the primary enhancement is on the downside with MLT larger than 3, then I call them a down onset. It's different from the previous ones. So combining the classification of SMU and SML, we have weak convection, strong convection, and down onset. So compared to the weak case in red, the strong convection cases in blue have higher SMU and SML growth in the growth phase, and they have stronger region 1 current enhancement, like here. And they have stronger and longer duration of southward MFBZ corresponding to stronger dayside reconnection rate. And they also have stronger solar wind speed. They also show a negative BY. So for this, I don't have a good explanation, but it's the clearest, the signature is clear. We also look at the MLAT near the onset time. Mostly they show 2 clusters at high and low MLT. And the events with strong convection had more cases at lower MLAT. It seems that with strong convection, the flux depletion can allow the current sheet thinning and substorm onset to occur at, closer to the Earth. And last, we look at the DMSP SUSI Aurora signature. This is a more typical substorm where the enhancement is near midnight, localized and strong. And then in this example, SMU and SML have very symmetric profiles with comparable amplitudes. The MLT distribution of SML, in this case, has a wide enhancements. The Aurora also shows enhancements in a wide MLT range. If you look at it carefully, then there are many small bursts, both in time and in MLT. So that reminds me this picture of the field and current wedgelets. It seems that these are the corresponding features in the index and in Aurora. So then this is the conclusion. Basically, we using the MLT patterns of SMU and SML, we can separate the convection from magnetic tail disturbance signatures, and that might be a helpful classification. Thank you.
questions in the audience?
Thank you, Dr. Shan, for a very nice presentation. Can you walk us through again with the local time distribution plots of the SMLs, where you differentiate between strong convection and dawn onset? Yeah.
Yeah, so for all of these, the primary enhancement is near midnight. So the difference is whether it has downside enhancement close to the onset time. Then for these three subcategories, for this one, there's no enhancement on downside, and the night side enhancement is also very localized. For this one, there's no additional separate peak here, but the primary enhancement can extend all the way to the downside. And then for this one, there are separate peaks in between dawn and the night side, but the downside signature occurs after the onset. So even though this might indicate convection, it's after onset. So for the strong convection, they both have separate enhancements between night side and downside, and the two either come at the same time or the downside convection occurs before night side signature. Is it clear?
Yeah, so we do not see most intense variation in the dawn for strong convection?
Right, so for that case, that belongs to the last.
The dawn
onset. Yeah.
Okay.
Because they might indicate an additional, the current wedge just develops on the downside, which is completely different.
Yeah, very interesting. Thank you.
Thank you.
Thank you so much. We're going to move to the last speaker, who's Mike Shumko.
All right. Hi, everybody, and thanks for sticking around. I know I am the last speaker between you and your lunch, so I will try and make a speed run out of my talk. So I appreciate you guys sticking around here. So I believe, as you guys already introduced, I am going to be talking about on the spatial relationship between the substorm aurora and relativistic electron precipitation during a storm-timed substorm. This happened during the now famous Eat an Extra Dessert Day. And actually, during this event, we had a auroral chaser, Gunjan Sinha, who took this really nice background photo that I discovered through Aurorasaurus that was taken right below where the substorm occurred. So it was a really cool study to work on, and hopefully you'll feel the same way at the end of this. So the overarching question that this case study helps address is, how does the radiation belt, plasma sheet, Satory boundary, and the ionosphere kind of couple during substorms? And for that, what I'm going to sort of prime the audience here and see if you guys, when you see the beautiful displays of the aurora on the ground through auroral images, where in the magnetosphere does the aurora originate from? And I know I gave this talk previously yesterday, and I know Larry especially had some thoughts about this from his decades of experience, but keep in mind, do you think it's happening in A, the dipolar magnetosphere, B, the transition region, or C, further out in the magnetotail? Which the answer was, for me at least, a little surprising once I found out. And to find out, we'll use the isotory boundary morphological mapping, which has been discussed before here, and this is a very nice 2 figures from Colin Wilkins' 2023 paper showing a very nice, pristine example of an isotory boundary that was observed by Elfin, which were 2 CubeSats, which I think we already discussed earlier here. And I guess the important part is the isotory boundary effectively is believed to map in the magnetosphere or magnetotail to this region called the night side transition region, or NTR. And so, all right, let's talk about this substorm event here. First of all, our cast of characters here, you have the Themis probes, which are really close to the neutral sheet, observing the temporal dynamics of the magnetotail and the sort of the transition region. You have the twin Elfin CubeSats, they're orbiting in low Earth orbit. And then you have the T-Rex RGB array of all-sky imagers here. And one interesting thing is I know a lot of people here are interested in the VLEO sort of measurements. And actually, 13 days after this event, Elfin A deorbited. And this time it was at an altitude of about 270 kilometers. So if you guys want to explore how satellites, deorbit close to their end of their mission, there's a few weeks or a month of good data from Elfin you can use for this. And a little background here, I'll be very brief here. It was very, geomagnetically driven configuration of the magnetosphere. You had, negative BZ most of the time, solar wind speeding up. You have this is the AL or the SML index showing a precipitous drop over here. This is where the substorm occurred, this vertical dashed line. And then on the right, you see the 3 panels showing the Themis locations in Y, X, and ZX planes using a T89 field model. And then you have the auroral projection of that on the ground where Themis, Themis probes mapped to over here in this mosaic of the T-Rex RGB images, and then Elfin flew through the field of view within a few minutes. And so at this time, around 420 UT, we had essentially a dipolarization. So this just shows the magnetic field from Themis, and pay attention to the green curve at the very top. It's very small. It's actually the smallest component of the magnetic field before the dipolarization, so over here. And after dipolarization, it becomes a dominant component, which is aligns with the dashed dotted black line here. And you can plot the same thing in the bottom panel using the magnetic field inclination to see that. And I like simple interpretations of like what the heck is happening. So here's a nice little illustration of the field becoming, going from more stretched to dipolar over about a 4-minute time period. And Themis is effectively stationary. So it effectively says the fields around it is dipolarizing really quickly. On the ground, this corresponded to, there we go, this substorm expansion phase. So there's a lot of experts here on substorms, so I'm not gonna, comment too much on this, except for you see this very bright arc on the poleward edge, and then the equatorial part of the aurora, it's more kind of like diffuse with some structure in there. I think that the altitude of the emission changes because you can see at some point between Rabbit Lake and Gillam, the top 2 images, the arc doesn't seem to line up, but it lined up more in the beginning. So anyway, it's a very dynamic event. And during this time, Elfin flew through the field of view. And just kind of give you a perspective, this is what a normal Elfin pass looks like without context of the auroral imagers. You see the plasma sheet over here is dominated by less than 200 keV electrons. They're fully isotropic, so that's all the yellow stuff here. And then we have this transition to here to a population that's about 2 to 3 MeV energies, and it's mostly isotropic at lowest energies, and then it becomes more trapped at high energy. So that's like more. So in the plasma sheets, more field line curvature scatter driven, and then at the radiation belts, so this region here, it's more wave particle interaction driven, given how the energy profile of the bottom panel here. The scattering efficiency becomes lower at higher energies. And then you have further intermagnetosphere stuff. And so when you add the imager context here, this is 4 different snapshots of the auroral data here. And as Elfin, the important parts is like as Elfin is entering the field of view here and exiting or entering the auroral region here and exiting the auroral region over here, that's when it sort of sees the beginning of the multi-MeV particle population here, and then ends it right here. So it actually doesn't line up with the trapped population, but if you look at the precipitating, it lines up exceedingly really well. So the high region of high scattering ends right there as it was leaving the expansion, auroral expansion region here. So I already described that. And so here's the animated version of this event here. Yeah, so same thing. So basically the radiation belt electron precipitation from hundreds of keV, sometimes to MeV energies, is 100% overlapping with the substorm expansion phase aurora, which at least to me was news. And this, actually 2 minutes later, we had even a better conjunction between POES and the T-Rex ASI. So same idea, same format here, different particle detectors. And the important part is that the solid lines here, that's the 0-degree precipitating electrons, basically increase around the time when POES flies into the field of view, and then as it was going through this arc up here, that's where it saw the isotropy boundary over here. So very similar rough profile that Elfin saw. So it's a nice confirmation that the sort of morphological mapping is consistent with two different very well-timed conjunctions. And here's the animated version of that as well. All right, and so our interpretation is effectively you had a magnetic field line that in the before time, Themis was close to the night-side transition region, seeing fairly stretched field lines, and then within 4 minutes, they dipolarized. And so initially, the source of the auroral arc was from somewhere from the NTR, and this based off of Viktor Sergeyev's 2012 and Nitin Sivadis' papers. And then afterwards, if the field dipolarized at Themis, that means that now the transition region is somewhere further out. And then this whole region from the dipolarized magnetosphere, that's where the source of the aurora and the radiation belt, less than 2 MeV radiation belt and isotropy boundary precipitation originated from. And so my question to you is how does a storm time substorm aurora correspond to the overlapping radiation belt and plasma sheet regions? And actually I gave this talk yesterday as well, and we had a really good discussion about the proton isotropy boundary and how the substorm onset likely occurs there. So my hypothesis that I was thinking of in the last 24 hours is I suspect, or I hypothesize, the expansion phase aurora in latitude to be the same extent as the difference between the proton and the electron isotropy boundaries. So if you can measure that from Elfin and then seeing how that corresponds to the aurora, it'll be, I think, fairly straightforward to test if there's data. There's a preprint, as you can see, so if you want to take a look at the draft version manuscript, you're welcome to. All right, thank you, everybody.
Thanks, Mike. Questions for Mike?
Well, it's more clarification, if you want. The fact that aurora coexists with multi-MeV particles doesn't mean that these multi-MeV particles has anything to do with aurora. Am I correct?
Yes, exactly. So they're spatially, so in your manuscript, we are being very careful. We're not implying causation. The radiation belt particles are not helping initiate the substorm. And if you actually look at this animation where the precipitation stops, it's not quite where the radiation, it's not quite the inner edge of the outer belt. So effectively it shows you how far in the, injection came in. So it didn't actually penetrate all the way to the inner edge of the outer belt. But yes, I think the radiation belt dynamics are independent of the substorm, but they do occur, as I hypothesize, occur in the same location.
Any more questions? If not, we're going to thank all the speakers, and I want to thank Vincent Ledina that has been taking notes during all the sessions, and Fumi, who is our student that has been helping the Meso focus group the whole week. Thank you, everyone, for staying so late.